Welcome to Elementary Functions. Today we're going to talk about phase shift and sinusoidal functions. My name is Wendy Fresh. I'm from Portland Community College and this is Math 112. The objectives for this lesson are phase shift versus horizontal shift, graphing and writing sinusoidal functions, and using sinusoidal functions to model data. On the next slide, you'll be exploring phase shift versus horizontal shift by graphing a couple of functions. Those functions are f of x equals 4 times the cosine of 2x, and g of x equals 4 times the cosine of quantity 2x minus pi over 2. Now you may already see that these functions are very similar. You'll use the Desmos calculator that I've embedded on the next slide to graph these functions. I'll also indicate what your window settings should be. Once you've got your picture, go ahead and click to the next slide to see if our pictures match and to see what sorts of observations we can make about the difference between these two functions. All right, let's begin with phase shift versus horizontal shift. The complete graph below is what you should have seen when you graphed on the Desmos calculator from the previous slide. Using your understanding of transformations, is this what you expected? So let's take a look at this graph. The first function was our 4 times the cosine of 2x, and that graph is being graphed in red. So a couple of things that I notice about that red function. The 4 on the outside of the function tells me that the amplitude is equal to 4, and the 2 that's on the inside of the function tells me that the period is 2 pi over that 2 for a period of pi. So let me take a look here. A normal cosine curve at 0 is at its maximum value, and that certainly seems to be happening on this one. For the red function, I see that my maximum point at 0 is occurring at 4, and that's my amplitude. Now, the next time that I see that repeat itself is pi units to the right. And that makes sense because the period of the function is pi. So I would expect the blue function to have those same characteristics, an amplitude of 4 and a period of pi. And that's because they have the same 4 on the outside of the function and they have the same 2 on the inside of the function. But what the blue function has is a minus pi over 2. Now, from what you know from previous classes, you should have expected that this created a shift to the left or the right. What is unusual, and maybe what you didn't expect, is that in this particular function, let's see here, I actually shifted. If I started at 0 and had a maximum of 4, my new blue function actually has a maximum at pi over 4. So where does that pi over 4 come from? Well, it turns out that in order to say anything about the horizontal shift of a function, what we have to do is we have to relate the inside of the function not to 2x, but just to x. So that means I need to factor the 2 out. And if I factor a 2 out of what is inside of the parentheses, I'm left with x minus pi over 2, but to account for that 2 that I just factored out, I have to put another one there. So this becomes 4 times the cosine of quantity 2 times the quantity x minus pi over 4. And it's that minus pi over 4 that is creating my shift to the right of pi over 4 units. So again, just like we saw with the period of the function, what we expect to see on the inside of the function, it ends up showing itself as the opposite when we go to graph it. So let's review what we just learned. In the functions, f of x equals 4 times the cosine of 2x, and g of x equals 4 times the cosine of 2x minus pi over 2, we found that the phase shift is pi over 2. In other words, the phase shift is the number on the end on the inside of the parentheses before we have factored anything out. And the horizontal shift is pi over 4. And that's the number we get once we factor. Taking that information and combining it with what we learned in the last lesson, we have the following definitions. Given a sinusoidal function of the form y equals a times the sine, and this little w here, again, it's just a Greek letter. This stands for omega. I could put anything there if I wanted. So y equals a times the sine of omega x minus c plus k, or y equals a times the cosine of omega x minus c plus k. The phase shift is c, and the absolute value of c over 2 pi represents the fraction of a period that the graph has been shifted to the right if c is positive, or to the left if c is negative. If we rewrite the function as y equals a times the sine of omega factored out, so now on the inside we have x minus c over omega plus k, or y equals a times cosine with the omega factored out, x minus c over omega plus k, we see that the horizontal shift is c over omega, and that is in units, whatever those units happen to be. So we would shift to the right if c over omega is positive, or to the left if c over omega is negative. Some math books call h the phase shift. We will define phase shift in the same way that physicists and engineers use the term. That is, phase shift is the value when the function is in unfactored form, or the value of bh. So let's take a look at an example. Identify the phase shift and the horizontal shift of g of x equals the sine of 2x minus 2 pi over 3. So what we have in this function on the inside is something that has not been factored. And what I mean by that is that on the inside of this function, instead of having just x, I have 2x. So I'm going to factor a 2 out to get the x by itself. And if I do that, out of that 2 pi over 3, the 2 that I just pulled out, to offset that, I put a 2 in the denominator. Now what this helps with is checking. If I were to multiply that 2 back through, we would see that I would end up with exactly what I started with. So I'm going to say that in unfactored form, g of x is what I started with the 2x minus 2 pi over 3. But in factored form, I have g of x equals the sine of, I've pulled the 2 out, and I'm left on the inside of the parentheses with x minus, my 2's cancel out, so I'm left with pi over 3. So I can say that the phase shift comes from the value that's on the inside of the parentheses before I factored, so 2 pi over 3, and the horizontal shift is coming from the value on the inside of the parentheses after I have factored, and so that becomes pi over 3. Now in the function above, the horizontal shift is telling us that the graph behaves like the graph of f of x equals sine of x, in other words, our normal or parent sine function, but shifted to the right, pi over 3 units. The phase shift determines how far out of phase a sinusoidal function is in comparison with the parent function, in this case f of x equals sine of x. To determine this out of phase amount, find the ratio of the phase shift and 2 pi, or in this case the ratio of 2 pi over 3 to 2 pi, which equals 1/3. This tells us that the function g of x is out of phase 1/3 of a period. So let's take a look at an example where we are graphing or writing a sinusoidal function. In this particular case, we are being asked to graph 2 periods of g of x equals the sine of pi x plus pi over 2 plus 3 without using a calculator, and by finding or using the amplitude, the period, the midline, and the horizontal shift. All right, so let's start with the amplitude. The amplitude is the absolute value of the number on the outside of the function being multiplied. In this case, there's nothing there, so we know that there's actually a 1. So the amplitude is 1. The period is 2 pi over my b value, and my b value is pi. So that reduces to 2. So the pi cancels out. My midline is y equals 3. Don't forget with a midline, because it is a line, you want to write it as y equals. And finally, the horizontal shift, we don't know at this point because our pi over 2 is in unfactored form. So let me just go ahead and factor a pi out of the inside, and when I do that, I get pi over 2, and I'm going to offset removing that pi by putting it in my denominator. And let's see, the pi on the top and the bottom cancel out, and it looks like I'm left with 1/2 as my horizontal shift. Now, because it says plus 1/2, I know that I'm going to do the opposite, so I will be moving 1/2 units to the left. So let's see if we can put that on a graph. So I've already put together this graph, and here's the way I like to think about it. Let me switch to a color, maybe blue, so we can see it. The first thing that I like to do is mark out the things that I know. First of all, I have a period of 2. So I'm going to go out to that period, which I see I've already made a mark, and I like to break that period up into 4s. So there would be 1, and I'm not going to mark 1/2, but there it is, and there's 3.5. And then since this one wants me to do 2 periods, there is another period of that function. All right, the next thing I want to do is I want to mark out the midline. In this case, that's y equals 3. So it looks like I'm hitting 3 about right here, right between 2 and 4. And then from that midline of y equals 3, I'm going to go up 1 and I'm going to go down 1, and that gives me my amplitude, or my most maximum or most minimum points. There we go. All right, so the next thing that we want to do is identify what type of curve are we talking about. And in this problem, this is a sine curve. So we have to go back to what we know our parent function looks like. What does a normal sine curve look like? Well, a normal sine curve at 0 is hitting its midline. So that's what we're going to do. The only thing that's going to be different is that we're going to take this function and we're going to shift it to the left 1/2 of a unit. And I'm going to do that first before I talk about anything else. So let me just mark off -1, because I think that's going to make shifting to the left 1/2 of a unit easier. So starting at 0, I'm going to put a point at my midline, moving over 1/2 unit. So it looks like I am at a value of -1/2. Now, the other thing that I know about a sine curve, actually any curve, is that wherever it starts, we're going to see that value again at the end of the period. Now, the period is 2, so normally I would go out to 2, but because I shifted to the left 1/2 a unit, I actually started early. So that means I'm going to end early as well. And then the other thing with the sine curve is that's not the only place where I hit a midline. I hit my midline where I start, where I end, and I also hit it halfway between. So I'm going to be hitting it right there. And I got that value just by going from my start 2 to the right and from my end point 2 to the left. Now, in between where I start and my middle value, I hit my max. And in between where I end in my middle, I hit my min. And so connecting those with a nice smooth curve, I get a picture that looks like that. Now that would represent one period of this function. Now, one of the advantages to marking off my period in 4s is that all I have to do is every single one of these points just move out 4 units and put it at the same height. So for example, this point that's at 1.5, and at my midline, I'm going to go out 1, 2, 3, and 4 units from that point and plot something. From my minimum value, I'm going to go to the right, 1, 2, 3, 4. Now I'm moving to the right. I could move to the left as well. From my midline, I'm going to move to the right 1, 2, 3, 4 units. And from my maximum, I'll go out 1, 2, 3, 4 units. And I think that that's probably enough for me to connect and see a second period of this function. So let's look at another example. In fact, in this section, we're going to spend a lot of time working examples because really the best way for you to get good at this is to be working lots and lots of problems on your own. And even though you'll see me in this example actually try to graph 2 periods of this function, make sure that what you're doing as you get comfortable with this is pausing the video before I start to work the problem, answering the questions, and trying to graph on your own paper. So what I'm being asked to do on this one is to graph 2 periods of the function q of t equals 2 times sine of quantity 4t plus pi plus 1. And you'll do that without using a calculator. And you'll do that by identifying some key things. The first is the amplitude. The amplitude is the absolute value of this number that I see multiplied on the outside of the function. The absolute value of 2 is 2. The period of the function is 2 pi over the absolute value of my b value. And my b value is this 4 that's on the inside. Now in the last slide, I think that I neglected to put that absolute value symbol there. And the reason I did that was because it was already positive, but in the event that that 4 were negative, it would not change the period. The only thing that we would see changed is possibly a reflection over the x or the y axis. And we haven't looked at one of those yet, but we will soon. 2 pi over 4 reduces to pi over 2. And let's see, the midline. The midline is the line y equals 1. That's coming from the number that we add or subtract on the end. And finally, the horizontal shift. I'm going to have to factor in order to see that. So I've got that q of t is equal to 2 times the sine. I'm going to factor a 4 out, and that leaves me with t plus pi over, and I'm going to put a 4 on the bottom to offset factoring the 4 out, plus 1. So my horizontal shift will be pi over 4 units, and those units will be to the left. So here's the graph that I came up with. And I'm going to mark off these things that I just found. My period is pi over 2. And so to mimic the 4 quadrants of the unit circle, I'm going to break pi over 2 up into 4 pieces. Halfway between pi over 2 and 0 is pi over 4. And then halfway there and halfway there. I can go ahead and put numbers on there if I want, but I really don't need to as long as I know their position. The next thing I'm going to do is mark out the midline. The midline is y equals 1. So I'll sketch that in. And then from that midline, I'm going to use the amplitude of 2 to go up 2 to 3 and down 2 to -1. Now, because I'm anticipating a shift to the left, let me also identify not only one period to the right, but maybe one period to the left. There we go. All right, so we are dealing with a sine curve, and from the last slide, the sine curve is fairly familiar to us. We know that normally what the sine curve does is that at 0, I'm at my midline, and that's what's going to happen here, but I'm not going to hit that midline until I shift my normal sine curve to the left pi over 4 units. So I get that point right there. At the end of my period, which is normally pi over 2, I would also be at the midline. Because I shifted to the left pi over 4, I have to do that for my end. And then we know in a sine curve, halfway between, we also hit the midline. Halfway between where I started and my middle value, I'm up at my maximum, which is at 3. And halfway between my end point and my middle, I am at my minimum value. So if I connect these points with a nice smooth curve, I get that picture. And that would represent one period of this function. Now, how do I find more periods of the function? Well, again, because I broke up that period into units of 4, I can just move out those 4 units. In other words, let's see, actually in this case, pi over 2 was 1, 2, 3, 4, 5, 6, 7, 8 units. So if I move out 8, my value at pi over 4 in the midline turns into 3 pi over 4 in the midline. And then of course I'm also there halfway between and up above. So you'll get so comfortable with knowing what this sine curve looks like that you really won't have to do any counting. Okay, so that's what the function q of t looks like. So now example 3. And it looks like in this example we have ourselves a cosine function. Graph 2 periods of f of x equals -2 times the cosine of quantity 2x minus pi over 2 plus 1. And as always, do this without a calculator and by using the amplitude, period, midline, and horizontal shift. By the way, I haven't done this, but you should do this on your own. Once you've done all of this work and you've completed a sketch of the graph, then go ahead and grab a graphing device, that can be your graphing calculator, Desmos, or GeoGebra, and confirm that what you plotted out is actually what the picture is supposed to be. All right, so let's answer our questions. What is the amplitude? The amplitude is the absolute value of this number on the outside. This is the first time we've seen a negative there. We'll talk about what that negative does in just a minute. So the amplitude is 2. The period of the function is 2 pi over the absolute value of 2, and that 2 came from right here. The number that's on the inside of the parentheses connected to that x. So I get 2 pi over 2. The 2's cancel out, and I'm left with pi as a period. The midline, remember it is a line, so it's y equals 1. And finally, the horizontal shift. Do I have to factor? It looks like I do. So I'm going to say that f of x is equal to -2 times the cosine. I'm going to factor the 2 out, and I'm left with x minus pi over, well, it was pi over 2, but now it's going to be pi over 2 times 2 to account for that 2 that I just factored out. And pi over 2 times 2 is pi over 4. And this time there's a minus sign in there, so that means I'll be moving to the right, pi over 4 units. Okay, so here is a graph, and let's see if I've got the values that I need. I have a period of pi, so here's pi on the graph, and I'm going to go ahead and mark halfway between 0 and the period of pi, so that's at pi over 2, and then of course halfway between 0 and pi over 2, and then halfway between pi over 2 and pi. And now I'm going to put in my midline, which is at y equals 1. So I'll just do a dashed line. And then my amplitude, I'm going to go up 2 to 3, and I'm going to go down 2 to -1. All right, now what's this curve going to look like? Well, in order to answer that question, I have to remember, what does the cosine function look like? At 0, a normal cosine function is going to hit its maximum value. So that's what we're going to do, only we're going to move to the right pi over 4 units to begin, and I'm going to put a point down. And let's see, I know that I'm hitting my maximum at the beginning and at the end of that period. And the end of my period is pi, but I moved pi over 4 units to the right. This is going to be a little bit hard to see because I've got an icon there, but I think I can squeeze it in. Hopefully you see that. 5 pi over 4, I'm going to go up to 3. And then halfway between those two values, I'm not at my maximum, but I'm at my minimum. So what is halfway between 5 pi over 4 and pi over 4? Well, let's see. I have a, if I were just to count, I would have 1, 2, 3, 4 tick marks. So it looks like if I go to the right 2 tick marks and to the left 2 tick marks, that puts me at 3 pi over 4, and that's going to put me at my minimum value. And then halfway between where I started and that middle value, I'll be at my midline. And halfway between my endpoint and my middle value, I will also be at my midline. Except, do you see the mistake that I made? I haven't talked about the negative, have I? We have a negative on this cosine function. Do you remember what a negative does? And if you don't remember, let me see if I can refresh your memory. Back in previous math classes, I bet you looked at things like y equals x to the second power. And then from there, you may have looked at y equals negative x to the second power. Well, what y equals x squared looks like is a parabola that goes up. And what we found when we graphed, this was from a long time ago, so hopefully I'm just refreshing your memory, when there was a negative on the outside, it took that parabola and it turned it upside down. As far as a graph goes, a rectangular graph, what that really means is a reflection over the x-axis. So here's what that means for my picture. I'm glad that I didn't sketch in any curve yet. That means that instead of me hitting my maximum at pi over 4, I would be hitting my minimum at pi over 4. So I'm going to put actually a point right here. That's going to be my minimum. And I'm going to hit that point again down at the end of my period, which is 5 pi over 4. And then instead of hitting my minimum at 3 pi over 4, I will hit my maximum. So here's what my curve actually looks like. That was a good mistake on my part because it's the sort of mistake that is really easy for you to do as well. I will leave graphing that second period up to you. And once you think you've got it, go ahead and compare it with a graphing device. So now let's look at another example. Now that you've had the opportunity to look at functions and try to graph them without a graphing device, let's do the reverse. Now you have a graph and you're being asked to find 2 algebraic rules, one involving sine and one involving cosine, for the function that's graphed below. The nice thing about this is that the technique that we're going to use is exactly the same technique that we used on the previous slides. In other words, what I want to do is analyze this graph and identify some of the key features. So I'm going to start out by identifying the period. That's the first thing that's popping out at me. The period of this function, I'm looking at 0, that I am here at my minimum value, and I don't see that minimum value again until I hit pi. That means that pi is my period. Now that's good to know, but in terms of writing a function, what I really need is the b value. So what I'm going to do is I'm going to take pi and set it equal to 2 pi over b. I'm going to cross multiply to get b pi equals 2 pi, and I'll divide both sides by pi to get my b value of 2. So that's the number that I will be using when I write my sine and cosine function, the number that will be on the inside. Now, how about, let's see, the midline. Well, the midline is the halfway point between the highest and the lowest value. Now, we already said that the lowest value is -6. It looks like the highest value is 2. In this case, if you want to just count from high to low until you get to the middle, you can do that. Another technique is to take the high value, add it to the low value, and cut it in half. So that gets me -4 over 2, which is -2. Don't forget that this is a line, and so we're going to say y equals -2. I'm going to go ahead and put a dashed line on here because I just think it's going to help me when I go to write my actual function. And then let's see, what is the amplitude? From that midline of -2, I would have to go up 2, or excuse me, up 4 or down 4. So my amplitude is 4. Now you'll notice I haven't done anything with positives or negatives, and I haven't talked about a horizontal shift. That's because depending on whether I'm looking for a sine or a cosine function, that's going to affect those values. So what do we want to start with? What I like to start with is, does this look most like a normal sine curve or most like a normal cosine curve? And whichever one it looks most like, in other words, without having to shift, I always like to start there. So to me, this looks most like a normal cosine curve with a small adjustment. So it is a function. I'm going to say that my cosine curve is f of x equals, now here's the adjustment. Normally at a cosine curve at 0, I'm at my maximum. This one, I'm at my minimum. And we saw on the last slide that when that reflection over the x-axis occurs, that it makes that number on the outside a negative. So I'm going to have -4, 4 is my amplitude, times the cosine of, now I'm going to put my b value, which is 2, and then x. Remember, I need an input and I need an output. Now, I don't have to do any sort of shift on this one because this does look like a normal cosine curve. The only thing I'm going to add to this is my midline, which is my -2. So there's a cosine curve, and I would encourage you to put that into a graphing device to see if it matches up. Now, how about a sine curve? I'll call this one g of x. And let's see, this is a little trickier. A normal sine curve at 0 is hitting its midline. Now we're not seeing this curve hit its midline until we get to pi over 4. So what we might say is that this is a normal sine curve that's been shifted to the right pi over 4 units. So we'll remember that, but for now the amplitude hasn't been changed, and we'll have 4 times the sine of, and then in parentheses I'm going to put that b value. And then I'm going to put another set of parentheses because I want to put the horizontal shift. Now we said this was a movement to the right. So I'm going to do the opposite of moving to the right by putting a minus there. And I'm going to put pi over 4. And then I'm going to put my midline on there. So that should be my sine function. Go ahead and graph this one as well and make sure that you agree with our answer. Now let's look at our last objective. Using sinusoidal functions to model data. This is example 6. A company sells Q of M 1,000 blankets in month M, with M equaling 0 being January 1st, and Q of M equaling 30 times the sine of the quantity pi M over 6 plus pi over 2 plus 70. Graph this function over 1 year and describe the practical significance of the period and the amplitude. What month sees the least sales? So let me put up a graph here. In preparation for doing this, I do want to answer a few questions because the first thing was to graph the function. And so like you've seen us do before, we want to identify our key features. What is the amplitude? The amplitude is 30. That's the number on the outside of the function that's being multiplied. The midline is y equals 70. And let's see, the period is 2 pi divided by pi over 6, which is the same thing as 2 pi times 6 over pi. So it didn't look real nice, but when we simplify it, we get 12. And then let's see, do we have a horizontal shift on this one? It looks like we do. Let me go up to this function, q of m, and I'm going to factor out pi over 6. Now, don't be afraid of that fraction. I'm going to take my pi over 2 and divide it by pi over 6, but that's the same thing as multiplying by 6 over pi, right? And so pi over 2 times 6 over pi, the pi's cancel, and 6 over 2 turns into 3. So we have a horizontal shift of 3 units to the left. All right, so let's see what this graph looks like, and then we'll talk about the practical significance of the period and the amplitude. I'm going to mark in my amplitude, or excuse me, my midline of y equals 70. There it is. My amplitude is 30, so my highest value is going to be 100, and my lowest value is going to be at 40. All right, now this is a sine curve, so we know normally in a sine curve at 0 that we're hitting the midline, and that's what we're going to do here, only we're going to shift to the left 3 units first. So here is -3 on my m axis in between -2 and -4, and I'll go up to 70 and I'll put a point there. My period is 12, so I would normally go out to 12, but because I moved 3 to the left, I'm going to move 3 to the left here. That puts me at 9. That's my midline. And then halfway between those two values, -3 and 9, that's a difference of 12, so 6 to the left and 6 to the right, that puts me at 3. I'm also going to be at my midline. Okay, so something like this. In between my starting point and my first middle value, I'm at my maximum, so it looks like that's at 0. I'm at 100. I'm going to go ahead and start sketching this in because I'm starting to see it. And then halfway between my endpoint at 9 and my middle value, which is 6, I'm at my lowest value. So let's see if I can get this picture. Something like that, it looks like. So let's see. What is the practical significance of the period? The period was 12. That was my m value, and they told me that m stood for months. So I would say that the practical significance of the period is that every 12 months, right, what does the period tell us? The period tells us how often we repeat. So every 12 months, my sales of blankets is going to begin to repeat itself, and that makes sense. If 0 is January 1st, then 12 months later, we would see the same number of sales. And then what is the amplitude? What's the significance of that? The amplitude being 30. I would say that the significance of that is that from an average number of sales, which would be my midline, that I can expect the sales of the blankets to not rise or fall more than 30,000 blankets. All right, now what month do we see the least sales? Well, that seems to be happening just from the picture at an input of 6. So what month is that? So we have to be careful and make sure we pay attention to how this was defined. We're used to 6 being called June because that is the 6th month, but in this case January 1st started as our 0 value. So if that's the case, January 1st is 0, February 1st, March, April, May, June, and we actually see that when M is 6, that we're talking about the month of July. And I think that I can buy the fact that in July, probably a company would see its sales dip to its lowest value. In this case, that would be 40,000 blankets. And finally, our last example, example 7. The London Eye is a huge Ferris wheel with a diameter of 135 meters, which is equivalent to 443 feet. It completes one rotation every 30 minutes. Riders board from a platform 2 meters above the ground, and we're being asked to express a rider's height above the ground as a function of time in minutes. So maybe I'll call this F of t. All right, and what I like about this example is that Ferris wheel reminds me so much of a unit circle. So you might think about that as we go through. And I'm going to answer some questions about amplitude and period and midline, but before I do that, let me just, this is going to be a very rough sketch, let me just get a feel for what's going on here. Along my horizontal axis is T, which stands for minutes, and along my vertical axis is F of T, which represents my height in meters. And I'll put some arrows on here. I hope that I've left myself enough room. I guess we will find out. All right, so what has happened here? So at 0 minutes, I'm getting on the Ferris wheel. So remember, this is my height above the ground. And so at 0 minutes, I'm on the Ferris wheel. It says that I'm on a platform that's 2 meters above the ground. So at 0, I am at 2. Let's see, how am I going to mark this off? I'll just go ahead and put 2 here. I can't promise that these are going to be equally spaced out, but I'll do the best that I can. So my very first point is there. And then I go around the Ferris wheel. It says that I complete one full rotation every 30 minutes. So let me go out to 30, and I will say that I am coming back down. So that looks like it is my minimum. Let me go ahead and mark that on there. Now, what's happening halfway between there? Halfway between there, after 15 minutes, if you want to look over at my picture, halfway from 0 to 30, I am probably at the very top. And if the diameter of this Ferris wheel is 135 meters, let me just switch to a different color here. If this is 135 meters, then how high off the ground am I? I would be the 135 meters that's the diameter of the Ferris wheel plus the 2 meters off the ground. And so I think that at 15 minutes, I would be up at 137 meters. Make sure that makes sense to you. So in between my high and my low is the diameter of the Ferris wheel. Okay, so that's got my low values and I've got my high values. All right, and now my midline. So without even calculating, I know my midline is going to be halfway between these two values. So let's see, I guess we're sort of talking about my radius. What is half of 135? Well, 1/2 of 135 is 67.5. So 67.5 from my high and 67.5 from my low. So remember that a midline is the value that is in between that high and low value. So if I take 137 meters and I subtract 67.5 meters, or I take 2 meters and add 67.5 meters, I believe that I should be at my midline. And I think that that is going to be at 69.5. So halfway between 0 and 15 minutes, it looks like at 7.5 I'm going to be at that midline. And then halfway between 15 and 30, I should also be at that midline. All right, so let me sketch in this picture. Notice they actually didn't ask me to draw a picture, but why am I going to this trouble? Well, because it's going to help me come up with a function. So there is my picture, and what type of curve does this look like to you? To me, this looks like a normal cosine curve that has been reflected. So let's answer a few questions. We said that the midline is y equals 69.5. We said that from that midline we go up and down 67.5, so that's my amplitude. My period is 30 minutes. That's how often I repeat. But remember that the period is 2 pi over b. So if I cross multiply, I'm going to get b is equal to 2 pi over 30, which is pi over 15. And if I use a cosine curve, I don't think I have to worry about a horizontal shift. So I'm going to say that my function is f of t, and I'm going to throw in that amplitude of 67.5. I'm going to put a negative on there so that it reflects it, times the cosine of my b value, which is pi over 15. I'm not going to use x because I called it t minutes. And then on the end, I am going to add my midline of 69.5. So go ahead and substitute that into a graphing device and make sure you get a picture like what I got, or better yet, make sure that at 0 minutes that you really are 2 meters above the ground, and make sure that after 30 minutes you're back at that value, and that halfway in between you really are at your highest point. If you have any questions about these functions, make sure that you ask or that you post your questions on the corkboard.